Let's talk about a few more similarities between money and energy. So there's some things that you can do with money that you can also do with energy, and I think it's useful to see the comparison. So you can transfer money. So what that means is, like, let's say you start with $10 and your buddy Joe has $2. So if you transfer some money from you to Joe, the result is that afterwards, let's say you transfer $8 from you to Joe. So then afterwards, no surprise, you'll have $2, and Joe will have the $2 he had before, plus the $8 that he got from you, and he'll have a total of $10. And you notice that in this case, the total amount of money stayed the same, because here we had a total of $12, here we had a total of $12. And it might even be that after some time that Joe might transfer that money to someone else, so maybe he'll transfer it to his friend Sally, and then maybe you have $2 and Joe has the 2 plus some of what you gave him, so maybe he has a total of 6. And we can say exactly then how much Sally must have, because she has to have whatever's left over. So she's going to have $4. So that way, you plus Joe plus Sally, and this also came from you originally, the total is still $12, just like we'd expect. And the same thing is true for energy. So what that means is that, for example, if you are transferring energy, let's say between a gas tank that you're using to heat up a pot of water. So here's the gas, and here's the water. So first of all, we're going to need a way to measure how much energy we have, just like we say dollars is the amount of money. And scientists use an amount that's called joules. It's spelled like this, but pronounced like jewel, you know, like a diamond or a ruby. So 10 joules, and let's say the water starts with 2 joules. We often just use the abbreviation J. And then we use the gas to heat up the water. This is going to be a transfer of energy. It's going from one thing to, or from one place to another place. And so maybe we'll use all the 2 joules of the gas, and it's going to work exactly the same as it did with the money. We're now adding some energy to the water, so that has 10 joules. So we start with 12 joules, we end with 12 joules. And that means that the gas has less chemical energy, and the water is now hotter. And what's going to happen after some time is some of that energy from the water might not stay with the water, because, you know, if you leave a cup of hot water in a room, that heat energy, that thermal energy, will spread out a bit. So let's put gas, water, and the air. And so here's the 2 joules left in the gas, and then maybe the water has a total of 6 joules. And that means that the water has also given up 4 joules to the air. But again, the total will still be the same. It's still that 12 joules. So you can see that when you transfer money, the total amount always has to stay the same, because you're just handing it off. It's the same when you transfer energy. And this has to do with our idea that we had, that all energy has to come from somewhere and go somewhere. Where did the water get its energy? It came from the gas. Where did the gas's energy go? It went to the water, and eventually went from the water to the air. But every last joule of energy can be counted somewhere, just like every dollar can be counted somewhere. So this is transferring from place to place. Now, another thing that you can do is, let me get green, here we go. You can also transform money, and this means to change the form of money. So this one is pretty simple. You start with a $10 bill, and you can change that into change. You could change that into a whole bunch of coins. Now, you've changed the form of the money, but I don't think I have to tell you that if you start with $10 here, you're going to still have $10 here. You've only changed the form, but the amount has stayed the same. Well, it's the same with energy. When we transform energy, and this happens all the time, so let's say we start with kinetic energy. Remember, that's the energy of motion. And let's say we start with 10 joules of kinetic energy, and we transform that into, let's say, gravitational potential energy. That's the energy that's related to height. We know that if we transform it, we should get 10 joules of kinetic energy turned into 10 joules of potential energy. Because once again, the total amount before and after has to stay the same, because all that energy has to go somewhere, all that energy has to come from somewhere. Same as with the money. Now, there's one case where it's a little bit harder to see that the total amount is staying the same, and this is related to something called dissipation. So dissipation of money, we wouldn't normally say that, but dissipation of energy is something we would say. And dissipation is just a fancy word for saying to spread out. Here's what this means. If you start with a pile of $10 in coins, you've got a whole bunch of coins here, you got $10. Well, let's say that we decide to take those $10 and give them out to all different people. So we find people who need that money. Maybe they're going to buy food with it. Maybe they're going to buy something fun with it. But we take that money and we give it all away to different places. Now, at the end, you're going to have in your own pocket, you're going to have nothing left. This money has been spread out. But if you could go around and count all that money, it still exists somewhere, and there would still be $10 somewhere. It's just that it's spread out. Now, the key difference here between this and the other situations is that if you transfer money, you can usually find a way to transfer it back. Because, you know, Joe could give you the money back. When you transform money from bills to coins, you could probably transform it back. But dissipation is different. Dissipation, this spreading out, is one way. So this cannot be reversed. So make it big. Cannot be reversed. Dissipation only goes one way forwards. And this is true for energy as well. So when we have dissipation of energy, a good example is that if we start with a cup of hot water, it has a lot of energy in it to start with. Let's say it has 10, we'll just keep using 10 joules of energy. But what happens is after some time has passed, that energy from the cup has spread out. And so now the cup, instead of having hot water, is going to have water that is cooled down. It's colder water. Maybe it has only 1 joule left. And all that energy has spread out to the different air molecules, different bits of air in the room. And now if you could go and count how much energy you added to the room, guess how much there would be. Altogether, the energy in the room plus the water is still going to be that same 10 joules. But just like before, to get that energy rounded up again, if we wanted to put that energy back in the cup, that's very difficult to do and really is not practical. And so this, once again, means that energy dissipation is a one-way process. And specifically, it usually happens when thermal energy or heat spreads out. This is energy that is dissipated, meaning we can't get it back. It's not gone. It's still in the universe. We've heated up the room with all this extra energy. It's still there, but we're not going to be able to use it anymore. We can't change it back the way that we would be able to change back potential energy back into kinetic energy, or the way we would be able to use the hot water to transfer that energy back. So this is an important idea here. Oftentimes when it looks like we're losing energy, it's really just being dissipated as heat. It's heat spreading out. In the video and the questions to come, you'll have a chance to put these ideas to work. This is a tricky concept, so if you want to come back and watch this video again, that might be a good idea.